Welcome back. So, last couple of weeks we have been discussing about various two-dimensional experiments. I have already discussed about COSY, TOXY, and other sequences and took several examples of that. Today, we will go to heteronuclear correlation experiment. This is called HETCAR. It is written as HETCAR. But I'm just giving you an idea. It is a correlation experiment, what we can get out of it. But remember, this HETCAR nobody is going to use. The improved version of that is called HSQC. That is what people are going to use. Okay. So we will use that as and we'll know how to do what to do with the HSQC later. But just to give you the information about what this HETCAR does is this. It is another correlation experiment similar to COSY, homonuclear COSY we saw. Only thing is there we got the chemical shift connectivity among the coupled spin in the homonuclear case. If one proton is coupled to another proton through chemical one, there was a correlation, you got cross peaks. But here in this experiment, it is a heteronuclear correlation. For example, you consider CH3 group, CH, there are two carbon coupled to two protons. In this heteronuclear correlation, I can see which carbon is connected to which proton. I can correlate the chemical state of a particular carbon to that of the proton which it is attached to. It is a beautiful information. For example, if I make the proton assignments, if I know what are the proton chemical shifts, I can use this experiment to make the assignment of the carbons. Which carbon belongs to which proton. Only drawback is it gives correlated to proton attached to carbons. If there are quaternary carbons, non-protonated, you will not be able to see that in this experiment at all. You will see only carbon peaks which are attached to protons. This is called heteronuclear correlation or called HETCAR. Of course, I took the example for proton and carbon. This is not the thing which we have to do all the time. This correlation can be between any two heteronuclei, that is between abundant spin and rare spin. That is an important concept I am telling you. Because here we adapt polarization transfer. We take the magnetization from one, of course, not in HETCAR, in HSQC. I mean, what we do is we take the magnetization from abundant spin, give it to low abundant spin, and then take back to high abundant spin and see. So that's why this is a very important thing you can do between any two abundant spin and less abundant spin. But in the HETCAR, it is a simple correlation experiment where you can detect the carbon directly. This is the HETCAR sequence, very simple pulse sequence. You apply 90-degree pulse on proton. This is a preparation period. You allow it to evolve for a time T1, and in between, of course, you can also put a mixing this thing where you are going to put inert polarization mixing so that polarization can be enhanced here also. And then here 90-degree pulse brings the magnetization to XY plane. In the T1 period, H1 magnetization precesses in the XY plane for a time T1. Polarization transfer takes place. Now you are applying the 90-degree pulse for detection, and at the same time you are applying 90-degree pulse for carbon, and you start seeing the carbon by proton decoupling. Okay, this is a direct detection of carbon. Remember, unlike HSQC inverse experiment where abundant spin is detected. This is a direct detection of low abundant spin. This is what we are going to see. So here it takes a 90-degree pulse, allow it to evolve for a time T1. After that, you for a small time delay, which is equal to 1 over JCH, 1 over 2 times the JCH, do the polarization transfer, enhance the signal intensity, and then detect the carbon 13 signal with proton decoupling. This is a simple pulse sequence of HETCAR. So, one important thing is it gives information about which carbon is coupled to which proton. It is done by inverting proton population and varying the transfer of polarization to carbon. Remember, selective polarization transfer we discussed, how we can enhance the signal intensity. Exactly, same idea it is done, but it depends upon JCH. You can have a coupled version and decoupled version also. So decoupled version can be done by putting in a refocusing echo in the middle of the pulse sequence. That's what. See, we discussed there what happens in the case of sequences like this. Immediately after polarization transfer, if you start collecting the signal, start doing the decoupling, the antiphase components will be there. It will nullify the gain what you have achieved. As a consequence, we can do some tricks to see that you get in-phase components which adds up and gives us to enhanced intensity. That's what is normally done. And without going into the details, this is the molecule is taken same. Look at what is 2-ethyl butyrate we analyzed. This is the this is the proton spectrum. This is the Hetcar spectrum. I'm sorry, this is the carbon spectrum. This is a proton spectrum. Projection is plotted on the top of it. And this is really the 2D Hetcar spectrum. Now look at this, what you are observing here. We analyze this, remember in the proton spectrum, this molecule. This is CH3 peak we know. This is one. And this is the proton axis. Go horizontally along this axis. You are going to hit a peak here. Okay? You are going to hit a peak. And then go vertically up. You are going to hit that peak. See, go vertically up here. You are going to hit this peak. Go horizontally along this axis. You will hit this carbon. This proton. So that means the CH3, these three protons attached to carbon, has a chemical shift here. Its carbon chemical shift you can get from here. The simultaneous detection of both the nuclei is possible. You can correlate the chemical shift information of the protons attached to the particular carbon. Now look at this one. This carbon, this is again CH3 group, which correspond to which one? This is CH3, F. It is F. Look at this one. This goes and gets. You see a cross peak here. That means this CH3 go horizontally along this axis. This is the proton chemical shift, and here you hit upon a cross peak. Go vertically, you will see this peak. This is a carbon peak. So this carbon chemical of this CH3 carbon is correlated with this CH3. You get the chemical sheet of this proton and chemical sheet of this carbon if you know this peak. Very easy. There is also CH2. CH2 is here. It is B. It is written. Okay. B. Look at this one. Go horizontal along here and then you go vertically up. See. Go horizontally here. You see this peak. Go vertically up. You see this peak. That means this carbon of CH2, this proton of this CH2 is correlated to this carbon. This is, if I take the CH2 group, its chemical shift in the carbon dimension is this, in the carbon chemical shift, in the proton chemical shift is this. So directly we get both the chemical shift information. So all the carbons which are directly attached to proton can easily be identified. So you can see this, and this is for CH carbon. This is the carbon proton chemical shift. This is carbon chemical shift. But if you see, there is one peak in the carbon spectrum. If you see the projection here, or the carbon spectrum on the top of it, which is no correlation at all. There is no correlation to any proton. Look at this carbon. It has to be this carbon because this carbon has no directly attached proton. As a consequence, in the Hetcar experiment, this carbon will not give rise to any cross peak. This is the important point you should remember. You get the peaks only for the carbons that are attached to protons in Hetcar. Okay, but it is a fairly difficult experiment, long time consuming experiment. For the reason you are directly detecting the carbon. See, direct detection of carbon, which is a very low sensitive nuclei, takes enormous amount of time. That's why this is an improved version called inverse detection, which I'm going to tell you later as we go ahead. So this is an important thing we should remember. But you notice one thing. This is also correlation experiment similar to your homonuclear correlation like COSY and TOXY. There, the spectrum was symmetric with respect to diagonal. Remember, this is the diagonal. The spectrum correlation peaks are symmetric with respect to diagonal on either side you will get. But here, first of all, there is no diagonal. Secondly, there is no symmetry between in the cross peaks because this in the homonuclear case, both the dimensions were chemical shifts of identical spread, spectral width of identical spread. So very easily you would get the cross peaks on either side and diagonal will be there. Here It is not like that. This is a carbon chemical shift, much larger, about 300 ppm. It's a proton chemical shift about 10 ppm. There is no question of symmetry, no question of diagonal, anything. So in the heteronuclear correlation experiment, you will not have a diagonal peak. First point, there is not there is symmetry with respect to diagonal like Cauchy homonuclear experiment, and you will not get peaks for non-protonated carbons. These are the salient points of Hetkar axis. This thing. So now look at the Hetkar spectrum of a molecule. This is a simple molecule called ipsanol. Okay, look at this. There is one, two, three. There are three CH3s here. One, two. There are two CH3, and I don't know what is third one. Third one is here. Something. CH, I think. Huh? So it is here. But doesn't matter. Look at this. This you can go along the vertical axis here. You get carbon chemical shift. From the same contour, dry horizontal axis, you will hit upon this, you will get proton chemical shift. Now this one. See, very interesting thing you should appreciate here is, in this region, believe me, there are two proton peaks hidden, which may be difficult for you to distinguish here because they are closely spaced, very closely resonating peaks. But on the other hand, if you go back, you see these two peaks are well resolved in the carbon dimension. That is the beauty. You can measure carbon chemical shift very precisely measure from the center of this peak you go and you will precisely get the proton chemical shift. That's the one biggest advantage of that. See, this is this one. Now, if you come to carbon 6 is attached to two protons. They are inequivalent, I think. See, you can see that one carbon peak, it is correlated to two protons. This information you can very easily get from the heteronuclear correlation experiment. Same way, proton is correlated to two peaks here. One chemical shift as far as the carbon dimension is concerned, but in the proton dimension, it has two protons. See, these two protons are attached to the same carbon, so it gives the same chemical shift in carbon. There are two different peaks in proton dimension. Like that, you can start doing the analysis like this, and you see the proton 10 again. Interestingly, it has got two peaks here, correlating to two peaks. Maybe they are non-equivalent here. So you can identify all the protons to all the carbons which are attached to very easily here. Of course, you can keep extending. Analysis of the Hetkar spectrum is very simple. Take the example of tetraacetyl glucose. There are 1, 2, 3, 4, 5, 6, only 6. This is ADCl3. You can forget it. You cannot get class peak because it's deuterated carbon, no protonated. So there is no peak for ADCl3. And you can count 1, 2, 3, 4, 5, 6, 7 carbons are there. Each carbon, you go along this axis and this axis, you can get proton and carbon chemical shifts very easily. Okay, analysis is simpler. And I wanted to show you even for a very complex molecule like this, see there are so many carbons present here in the proton dimension. No, this is carbon dimension. This is the proton dimension. And in the carbon dimension, you see so many peaks are present. But we are able to assign each and every one of them. That is the beauty. Okay. There is another experiment called Kolak experiment, similar to heteronuclear correlation, where it is a correlation of long-range coupling via this thing, long-range coupling. Correlation between proton and carbon, heteronuclear correlation via long-range coupling. For example, in the previous experiment, what did you observe? There was a correlation of carbon to directly attach proton. That is Hetkar. But now this carbon can correlate to this proton, and this can correlate to this carbon, and this correlation we can subtract, we can eliminate that and do an experiment where you can get correlation peak only for the carbons which are coupled to remote protons. That is also possible. That type of experiment is called a Kolak experiment, called correlation via long range coupling. For example, two bond coupling between proton and carbon is there, that can be correlated. Three bond coupling between this carbon and this proton can be correlated. But mind you, it's the most difficult and time consuming experiment because you are trying to correlate the long range correlation. And this will be, of course, you may ask me a question, what happened to one bond coupling? We can efficiently suppress that while doing the experiment. Okay. But sensitivity is a very low experiment in this case, very low sensitivity experiment. So it is not easy for doing this. So Kolak, this is the pulse sequence, and you can understand this is a very nice experiment as You can go back and see similar to your Hetka experiment. Only thing you are going to put a delay here with small delay just before and after this pulse. So that delay you can choose, optimize this for the smallest chemical shift. I'm sorry, smallest coupling between proton and carbon. And once you adjust this delays delta 1 and delta 2 corresponding to smallest, of course the different carbon may have a different coupling with proton, but smallest 2 bond and 3 bond coupling approximate value you should know, and optimize that delay. You could one half of the J coupling for the delta 1 and one third of J for this one. You can establish long range correlations. Okay, I'm not showing that spectrum. Now I'll go into what is called inverse spectroscopy. What is inverse spectroscopy? That is something very, very important to know. For example, if I want to detect the X nuclei, which is less sensitive, you know that. I want to detect carbon, I have already told you, so sensitive, less sensitive, it takes enormous amount of time to get the carbon with the same amount of signal to noise ratio as that of abundant spin. On the other hand, if it indirectly detected through protons, how is it? What will happen if it is a trick we adapt? Take the proton, give this magnetization to carbon, again take it back. In this process, you can get the information from this carbon. Now we are detecting proton, not carbon. Our detection of proton is much better. You can get the spectrum in less time. That is the advantage. This is called inverse detection of carbon through proton. These experiments are called inverse experiment. Whatever the experiments, I said Hetkar, Kolak, etc. for long range correlation, same experiments you can do in a much faster time with better sensitivity by using inverse detection. Okay, this is a very important experiment, and what is important is the tremendous gain in sensitivity due to high gamma of the proton. Proton has a very high gamma. Transfer the magnetization of proton to carbon and take it back. The beauty is direct detection of carbon may take almost half a day to 1 day. Whereas if I do this inverse detection by HMQC, HSQC, I will tell you what it is soon. Then you can do the same experiment in less than 2 hours. Nowadays, even less, even you can get in 30 minutes, you will get it with a specially designed probes and high frequency spectrometers with a special pulse sequences, everything. You can get it even faster. You can get in less than 30 minutes now. See the advantage. We have taken the benefit of large magnetization of proton and use it, give it to carbon and do the inverse detection. And this is the beauty. See, it takes the advantage of the reverse inept transfer. What you will do is, you will first do the polarization transfer from proton to carbon. Then do the reverse inept transfer. Take the magnetization back to proton. And now we can directly detect the proton. So we have combined this with varieties of decoupling sequences like Waltz, GARP, MLEV. These are all pulse sequences used for decoupling. I told you about heteronuclear decoupling by CW. I also mentioned, I think there is GARP and Waltz pulse sequences are there where you can apply this for decoupling. So finally, all these decouplings, when you do this first inept transfer and reverse inept for transfer, and while detecting the proton, you can also do decoupling. This is a pulse sequence. Very, very easy to understand. This is a preparation period. Apply a proton 90 pulse and up to this what you know. It is evolution and you are going to do the take the magnetization from proton to carbon, from carbon to proton back and then start detecting the proton while doing decoupling of carbon. Very interesting, right? When you are detecting carbon, you are decoupling proton. Now we can do the reverse. This is the inverse pulse sequence for most of the inverse experiment. This block remains same. Take the magnetization from proton to carbon and how it works. We already discussed in the heteronuclear these inept sequences already, how the inept works, everything. Vector diagram we understood, So I don't want to go into the details. I hope you are all with me. So 90 degree to 180 and then transfer the magnetization here to carbon, carbon to bring it back to proton, again take it to proton and detect the proton while doing decoupling. This is the simplest pulse sequence used in inverse decoupling, inverse detection. Okay. In the two-dimensional experiment, in this detection dimension to this proton, I have been telling you. Now we have three classes of experiment which we can discuss here. One is HMQC, heteronuclear multiple quantum coherence, HSQC, heteronuclear single quantum coherence, HMBC, heteronuclear multiple bond coherence. And the HMQC and HSQC are more or less similar and they gave the similar information, except that there are some technical advantages of this over this. That's the advantage. Apart from that, the information content in both is same. Okay, that is the important point you should remember. Whereas HMBC gives you long range correlations. How do it does? We will see that. How we can do inverse detection. All this inverse detection experiment can be correlated to direct detection. There is a similar experiment for direct detection. HETCAR was there, I told you HETCAR pulse sequence where proton carbon was correlated. That is analogous to inverse detection sequence called HSQC and HMQC. There is a experiment called COLAC, correlation of long range correlation. Okay, long range coupling, correlation of long range coupling. That is an experiment where 2-bond, 3-bond proton carbon couplings can be correlated. Protons and carbons can be correlated, which are 2 to 3 bonds away, instead of directly bonded in HETCAR. This experiment is analogous to that, is called HMBC. Please understand, we have HETCAR experiment where direct correlation between proton and carbon of directly bonded nuclei, carbon and proton can be detected. You can understand if CH is coupled, carbon chemical sheet and proton chemical sheet of that attached proton and carbon, we can get easily. That correlation is obtained in the HETCAR experiment. In the COLAC, this carbon it can be having another 2 bonds away, another carbon or 3 bonds away. This proton correlation we can obtain. This is a long range 2 to 3 bonds away correlation can be obtained again between carbon and proton. But similar experiment is possible by inverse detection called HMBC. Okay, as I said, HSQC uses SYNAPT during evolution time and HMQC experiment makes use of multiple quantum pathway. This is where it is very difficult for you to understand when you have a multiple quantum pathway by energy level diagram. It's a little bit difficult to do, but it's not extremely impossible. Okay. So this is what I wanted to tell you. HSQC is routinely followed. It uses inept polarization transfer during evolution time. Please remember, inverse detection is what you have to do. If you are doing the proton-carbon correlation, if you have a molecule, if you want to analyze carbon spectrum and want to know which carbon is coupled to which proton, don't do HETCAR experiment or COLAC experiment. Please do HSQC. Directly bonded carbon protons can be correlated. If you want to get correlation, if you want to identify carbonyl, which carbonyl is 2 bonds or 3 bonds away to a proton, do long range experiment, that is HMBC. Then you can even get information about carbons which are not directly attached to proton but remotely coupled. Then you do HMBC. Except this inverse experiment, please don't try to do any direct experiment. That is no more advantages and now nobody practices that. Pictorially, this is what it is. Carbon proton 1 bond coupling is obtained by HSQC 1 bond correlation. And I have, let us say, 10 carbons or 5 carbons here. 5 carbons attached to a proton. I am going to get 5 peaks in the HSQC experiment. In the carbon dimension, you will get this chemical shift. If in the proton dimension for this cross peak, if you go, you will get this chemical shift. So for each cross peak, and if you go on F1 dimension and F2 dimension, correspondingly, you get chemical shift information of the carbon and corresponding proton chemical shift. But if you have a nitrogen proton like this, remember, that is also possible. You can do nitrogen 15 HSQC, especially finds very useful in biology, where they are dealing with proteins and peptides. Lot of NHS are there. They can do HSQC, nitrogen 15 proton HSQC, where they can correlate nitrogen 15 chemical shift to the proton which is attached to it. Okay, now if you come to HMBC, it gives connectivity between remotely coupled heteronuclei. For example, this carbon correlation to this can be seen, and this proton's correlation to this proton can be seen. This is of course 1 bond. I'm sorry, 2 bond. This is 3 bonds. So three bond correlation. Up this is excluding this. We can do an experiment to suppress this type of correlation. In the long range correlation experiment like HMBC, you can suppress directly bonded carbon proton correlation peaks. You can detect only this. They are called this is HMBC experiment where you get long range correlation, remotely bonded carbon proton correlation can be obtained. Now, I will try to bring into you the information about, we will try to analyze what is called proton decoupled and proton coupled HSQC and HMBC experiment, in which case you need to get some idea about proton carbon couplings in the proton spectrum, which we already discussed. You know what are satellites I discussed? If I take a simple example for CHCl3, simple molecule, I must get a single peak for proton. It's a doublet. Why it is a single peak? Because 99% of the molecules are in carbon 12 state. They exist as carbon 12 isotopomer. So it gives a single peak because it has no magnetic moment, so no coupling to proton. But remember, 1% of the molecule has carbon 13. Okay? 1% of the molecule. This is the carbon 13 observation. If I come to proton observation, you will see this is the carbon 12 peak and two satellite peaks. So when I observe carbon 13 here, carbon 12 is invisible. I decouple proton, I get a single peak. If I don't do decoupling, I'll get two peaks. Measure the separation. This exactly matches this separation. This is CH coupling. You can detect in the carbon coupled spectrum. Because we do the decoupling, generally, we don't see the coupling, we have single peak. But in the proton, you see carbon coupled to proton and you see as satellites, 1% intensity peaks. 1% further divided into 2, it is 0.5% intensity peaks are seen. This is in the proton spectrum, you see proton as satellites. Okay, carbon proton couplings are satellites. Fine. And this is 99% intensity peak. These peaks are 0.5 intensity peaks. This I wanted to tell you to get an idea. This you knew, but I repeated it to make you clear. What we are going to do is, let us look at the coupled and decoupled spectrum of HSQC, HMQC and HMBC. If you understand HSQC, of course HMQC is similar. Let us not worry about it. At least you should understand how a HSQC of coupled carbon 13 proton and decoupled carbon 13 proton spectrum looks like that. Similarly for HMBC. This is very important for you to interpret the heteronuclear correlation spectra like HSQC and HMBC. You must have an idea how to analyze this. Now, HSQC and HMQC, as I said, always utilizes one bond coupling. No need to repeat that. And HSQC, HMQC gives a similar information, but for technical reason, this has a signal to noise ratio different. That I told you, no problem. Now coming to HMBC. What does HMBC do? Yeah, I told you, again it keeps correlated over 2 to 3 bonds away. This is the basic pulse sequence for HSQC. Can you notice some similarity with what we discussed long back? Couple of classes back, we discussed this one. If you understand, you carefully see what is this. Does it not look like your inert black? Exactly. Then this looks like a reverse inept. We can do this. What it does is, it consists here, this pulse sequence is very simple. Here we take the polarization from proton, give it to carbon, and then after certain time, T1 by 2 in this evolution period, you will ensure the magnetization is taken back to proton by reverse inept. One is a forward inept, other is a reverse inept. In the process, what you will do is, you will take the magnetization from proton, give it to X nuclei, from X nuclei take it back and give it to proton. Now we are decoupling carbon and detecting proton. Why I have to decouple carbon when I am seeing proton? Carbon is only 1% abundant, right? But these satellite peaks are the ones which will be seen in the correlation experiment. We have to avoid that. Okay? That's why I showed carbon 13 satellites in CSCl3 spectrum. You understand basic pulse sequence. We already discussed the inept sequence by vector diagram. You can continue to do that. There is no problem. Or if you don't worry about the way magnetization behaves and all those things, how the spin physics, don't bother. Please remember, in this block, we take the magnetization of proton, give it to carbon. In this block, we take it back from proton to carbon. I'm sorry, carbon to proton, and then start seeing the proton signal while doing decoupling of carbon. We observe proton, decouple carbon. That is the interesting part of this experiment. Inverse experiment means we detect proton and indirectly get the information about the coupled carbon. Okay. Basically, look at this one. This is the flow chart. In both HMQC, HSQC, or HMBC, whatever the mechanism you try to do, of course, here is the polarization transfer mechanism in these two. What we will do is, what we do here is, you take polarization from I spin, transfer to S spin, allow it to evolve during T1. Then do the reverse polarization transfer to I and detect. Very simple, two steps, that's all. Nothing more. Fantastic, but this experiment is so good and so powerful now. Everybody does only this. PETCAR experiment is no more practiced. It's all outdated now. Only for academic interest to understand the concept, we do that. Otherwise, experimentally, it is not done anymore. Okay. Now, let us look at the carbon 13 proton HSQC spectrum. I consider a simple molecule like this. Now I will consider a situation because I have to look at the carbon 13. In this molecule, there are several isotopomers. In some portion of the molecule, let us say carbon 13, Ca will be in carbon 13 state. Ca exists as carbon 13, then Cb will be carbon 12. Obviously, joint probability of both of them existing as carbon 13 is very, very low. That we discussed already. In some of the molecules, that is one type of molecules we get. It is one type of isotopomers we call. In some portion of the molecules or of the sample, carbon Cb, carbon B will exist in the carbon 13 state and carbon A exists in carbon 12 state. That means you have two different types of isotopomers present. That's all we discussed. Remember in carbon 13 NMR, individual carbons, isotopomer spectra only you will get, and final spectra is the superposition of all of them. That's what I said. Exactly here also. Now we have taken this molecule as an example, but remember when Ca is 13, Cb is C12. When Cb is 13, Ca is C12. Both joint probability is very less. Okay. Now in the HSQC spectrum, what happens? In the F1 dimension, Ca gives a peak for carbon. F2 dimension, you get proton peak. That's what it is. That is correlation is like this, right? If you get carbon here in the F1 dimension, or let's say in this F1 dimension, this is carbon. In the F2 dimension, this is proton. That's all. I said in the HETCAR experiment, we got a cross peak like this, You go vertically up, you get carbon chemical shift. Go horizontally, you get proton chemical shift. That's what we get. But now, if it is a coupled HSQC, not decoupled, there is a coupling between carbon and proton. But in the carbon 13 dimension, its detection is easy. In the proton spectrum is what? They are satellites. Two peaks. That is a J coupling is there. And they come as small chota peaks as satellites. That is what it is. Okay? In the carbon 13 NMR, carbon 13 dimension, when this carbon is coupled to this proton, it will be a satellite doublet. Okay? Similarly, this one also will be a doublet in the proton dimension appear as satellites. Okay. See, in the carbon dimension, you will get chemical shift of carbon. In the proton dimension, you get chemical shift of proton. But in that dimension, you have a doublet which gives you proton-carbon coupling. Let us see the spectrum now. Very easy. Look at this one. Now, this is the carbon 13 chemical shift. Okay, if you go along this axis, this is Ca, carbon A. Okay, now look at this carbon B. If you go along this axis, you get only one peak. So this corresponds to carbon chemical shift. But let us go to proton dimension. This is the proton dimension. This is the proton peak corresponding to C12 carbon. And look at it, on either side you are getting a peak. What are they? These two are satellite peaks of this proton coupled to carbon, which appear as a satellite because we are doing coupled HSQC. Similarly, for this proton B, you have two peaks on either side, they are satellites. Understand? These two peaks are satellites for this carbon. These two peaks are satellites for this carbon. So center of this gives you this proton chemical shift. Center of this gives you proton chemical shift. And this is difference is J coupling. This difference is J coupling between carbon and proton, carbon A and proton attached to it. This is the J coupling between carbon B and proton attached to it. This is the coupled carbon 13 spectrum. So in the F1 dimension, you are going to get satellites. Carbon coupling is there in the proton, which appear as satellites in the proton dimension. Whereas in the carbon dimension, you get a single peak, nothing else. Okay, so you get this thing. And these doublets are nothing but carbon 13 satellites. Now, okay, we'll talk about HMBC now. What will happen to the HMBC? We'll see quickly, we'll do that, although time is up. Now, in the heteronuclear multiple bond correlation, what we should do, what we have to see, this carbon should correlate to this proton, and this carbon should correlate to this proton. That is called long range correlation. Exactly. If you look at this carbon 13 chemical shift here, earlier you got a doublet here, okay, corresponding to one bond carbon proton correlation. But now that is suppressed. What I am seeing is long range correlation. So this carbon A gives a peak at carbon B position. Proton B position. You see, this carbon A come horizontally, go vertically up, you see proton B. This is carbon A. It is attached to this proton, but it is giving correlation to this proton. That is called long range correlation. This is multiple bond, 1, 2, 3 bonds away. This carbon is giving correlation to proton, which is 3 bonds away. Similarly, CB is giving correlation to 1 to 3 bonds away, this proton. So CB, this is the chemical sheet of carbon B, but you go up vertically like this is correlating to proton A. This is a long range correlation. Carbon B giving correlation to proton A. Here carbon A giving correlation to carbon B. So this is proton B. This is a beautiful experiment. You understand what is happening here? You are getting long range correlations very easily. HA gives correlation to CB. This one. HA gives correlation to CB. HV gives correlation to CA. And direct correlation peaks are suppressed. No peaks here. This is what is called heteronuclear multiple bond correlation. Now, this type of information, we can come back again. I'll continue further in the next class. Let me see what is there to solve. Okay, the one slide I'll explain in another 1 or 2 minutes. Now, in reality, of course, there are two different experiments. If it is plotted together, how it comes. This will make your doubts clear. Now in HSQC, what you are going to see in the carbon dimension is very clear for you. This is carbon A, carbon B, and just go across this, you get carbon chemical shift. Done. This doesn't matter. Now, in the HSQC experiment, you get two peaks, coupled HSQC exactly at the center. Similarly, for carbon B, you get two peaks exactly at the center. What are these? These are proton carbon coupling which are directly bonded. This CB coupled to this HB gives you this doublet. This CA coupled to this HA gave you doublet. This is a coupled HSQC like satellite peaks. On the other hand, if I look at HMBC, this CA gives correlation to HB, this CB gives correlation to HA. Both are different experiments. Just for comparison, just to make you understand, this is shown here. I hope it is clear for all of you. Okay, these are two different experiments. Just suppose for comparison. Remember, HSQC gave you direct correlation to directly attach carbon proton. Similarly, but in this coupled case, In the F2 dimension, it's a doublet because of carbon-proton J coupling. This is what we observed in both the carbons. But in the HMBC case, carbon A correlates to carbon B, carbon B correlates to carbon A correlates to proton B, carbon B correlates to proton A. You may ask me, this is also coupled HMBC, why there are no peaks? Why there are no split multiplicity or satellite peaks? In principle, we should see that the coupling is of visible, is measurable. If it is very small within the layer, you will not see other way, most of the time. So it should be in principle possible to see because it is not a decoupled HMBC. Okay, with this, I will stop today. We'll come back and then continue with HSQC. Then we go to J couple, J result experiment, both homo and heteronuclear. And I don't know whether I have time to talk in more NOC. I'll come back to that NOC later. And then there are a lot more things we can talk. You can talk about inadequate, adequate experiment like that. Inadequate is to get carbon-carbon correlation, carbon in the natural abundance. That most of the time you don't require that. So I don't think I have time to talk about it. Next, I'll continue this with the decoupled HSQC and HMBC. How do you get the cross peaks? And then I will talk about some one or two examples of J result experiment. Let us see how we proceed further.